All right, welcome everybody. This talk is Reflected Intelligence, leveraging Lucene and Solr as a self-learning data system. For those of you who don't know me, my name is Trey Grainger. I'm the SVP of Engineering at Lucidworks, formerly Director of Engineering over Search at CareerBuilder. Other information you can look up online about me. One interesting thing, I am co-author of Solr in Action with Tim Potter, and I've got a couple of copies here Manny gave us to give away. I'm going to give them away to whoever sends out what I think is the most interesting tweet about this talk. So if you guys take pictures, tweet, what have you, if you don't have a copy of the book, that's a good way to get one. I'll talk more about that at the end. The talk today on reflected intelligence, the description was pretty impressive. The talk hopefully will be close to as impressive as the description. But what I want to talk about is going from a traditional basic keyword search, which everybody starts out with Lucene and Solr, and kind of moving up the curve of intelligence. When you start with basic keyword search, you think about things like the inverted index, scoring with TF-IDF or BM25, the query formulation. How do you formulate your query to best represent the search engine to get good results? And you eventually start moving up that curve of relevancy. You start thinking about things like taxonomies and entity extraction. How do I identify the items in my domain? And how do I both identify them in the documents and at query time, how do I extract them? Moving further up the curve, you have things like query intent, where you're trying to classify the type of query being asked. Is this a question about the news? Is this a question about the weather? Am I looking for information about a person, place, or thing? Or is this just a search and I just need to return some documents? There's also concepts like disambiguation and those kinds of things, which we'll talk about in a bit. Moving further up the curve, you've got concepts related to relevancy tuning. Specifically, how do I take feedback from users and incorporate that to make sure I'm returning the right results at the top? How do I incorporate data analysts and their opinions into my ranking calculation? How do I leverage more advanced techniques like learning to rank to build a classifier that can actually rank more relevant results higher based upon numerous signals? And then a little bit higher up the curve, potentially, which is what we want to talk about today, is self-learning. Having the system be able to learn from your data, from your user interactions, and almost tune itself. So that's what I hope to dive into in a little bit. Some of the key technologies, so I'll warn you ahead of time, this will be a bit of a whirlwind in terms of a combination of previous talks I've given that are in the public domain, that some open source projects that I've worked on, that other people have worked on, and so we're going to go through a lot of concepts in here. A few of the key technologies I'll highlight at the beginning. Obviously, you don't need to tell you what Lucene and Solr are. Those are key to all of this working. For the taxonomies and entity extraction part of that curve, I want to talk about the Solr text tagger, Word2Vec, and actually Simon Hughes at DICE has a really cool conceptual search plugin that's open source. I'm going to talk a little bit about, as well as the Solr RDF plugin for Solr, which allows you to search, RDF triples. Moving further up the curve with query intent, there's a probabilistic query parser, which is an open Solr issue right now, as well as the semantic knowledge graph, which is something that CareerBuilder recently open sourced. I've talked about it a bit in the past, but it's a really cool capability, and I want to give you guys an idea into how it works and what you can do with it. And then on the relevancy tuning side, I want to talk about learning to rank and ultimately how you can leverage your user feedback and content within the search engine to be able to power a lot of these capabilities. So the first question is, what is a reflected intelligence? In the context of this talk, reflected intelligence is leveraging any previous data or interactions to improve how new data and interactions should be interpreted. So when someone comes to your search engine and runs a search and gets some results and keeps clicking on the fifth result, that fifth result probably is more relevant than the first four. Those are some general intuitions that you could figure out if you're mining your query logs, things like that. Also, the content within your search engine. There's a lot of information in terms of the number of documents and the number of terms are used and how they're used within your documents. Excuse me. That can also be mined to leverage some really cool insights. So we typically talk about 3 C's when it comes to relevancy. content, collaboration, and context. Content is the documents within your search engine and the terms that are used to run searches. Collaboration is how people interact with your documents. And context is what you know about the users who are coming to run searches and how you can leverage that to adjust relevancy. So I'll try to keep the conversation within the context of those three, but each of those are going to be really important for measuring and improving relevancy. And critical to this is the idea of feedback loops, which I brought up just a second ago. The idea that a user runs a search, sees some results, takes an action, and then based upon the action they took, the system can then learn what to do the next time. That continues on and on with hundreds or thousands or millions of users, and over time your search engine continuously learns and adjusts as needed to give you the highest relevancy possible. Some examples of reflected intelligence include building recommendation engines, building user profiles from past user searches, clicks, and other actions, identifying correlations between keywords and phrases, building ontologies automatically, or a lot of people do it manually, but there's ways to do it automatically from content and queries, determining relevancy judgments using precision, recall, discounted cumulative gain, some of those techniques from click logs, learning to rank, which is building a ranking classifier to be able to take into account many features within your documents that your queries are trying to match, identifying misspelling, synonyms, acronyms, and related keywords, disambiguation of words that have multiple meanings, and otherwise just learning what's important within your content for a specific domain. So when we look at this curve, where people start with basic keyword search, move to taxonomy and extraction, and all the way up the curve, my hope is that once you get to the top, it's actually informing all of the other levels. So by mining query logs and understanding user interactions, you're able to better tune your relevancy because you can derive relevancy judgments from your end users. You're able to better figure out the query intent, taxonomies, and even improve basic keyword search, leveraging all of that information. So let's start with traditional keyword search. I'm going to blaze through this because I think this is an intermediate talk, so I'm assuming everyone's pretty familiar with Lucene and Solr. This is your basic inverted index structure. You take documents, you index them, and you end up with, on the right, your inverted index where all of your terms map to documents. When you go to run keyword search, you then look up each keyword as part of your search. So in this case, I searched for Apache Solr. I looked up Apache and found all the documents it's found within. Solr found all the documents it's found within. I do a bit set intersection or document set intersection of those two, and I find that document 1, 3, and 4 are the documents that match the search Apache Solr. Most of you guys should be with me thus far. You then take the resulting documents that match that query and run them through a relevancy, a similarity calculation. This one right here is classic similarity, TF-IDF. In Solr 6, we've now moved to BM25 as the default. It's still based on TF-IDF, so the general concepts still apply, but I should probably update this slide pretty soon. It's still TF-IDF. You do some adjustments based upon the average document length and K parameter and some other things, but it's more or less the same concept. It just works better. So general ideas with TF-IDF, term frequency is describing how well a term describes a document. IDF is how important is the term overall. So if someone runs a keyword search for an experienced Solr development team lead, the user would be really unhappy if all the documents that match, if the ones that came up at the top are the ones that match the word "and" the most, A-N. That's not what they were looking for. The most important word there is Solr, probably followed by lead, and then you kind of work your way down from there. And that's based upon IDF, which is the core concept to relevancy ranking when you're doing basic keyword search. But basic keyword search can't hold a candle to what you can do if you've got some domain knowledge in terms of what your users actually care about. So in the case of a new search engine, you probably care a lot about proximity and freshness, and those should be driving relevancy. For a restaurant search engine, you probably care about geographical proximity and price range. For e-commerce, likelihood of a purchase, or even amount of a purchase is probably key. For a movie search engine, more popular titles are probably going to be more significant than just any matching title. For a job search engine, you're going to care about the category of the job, the salary range, and geographical proximity. Those are all going to be key to what you're doing. So if you're solely relying upon TF-IDF or BM25 to do your relevancy ranking, you're not going to be coming anywhere close to matching what your users are expecting from your search engine. And so here's an example from Solr in action of this in practice. These are a bunch of people who are looking for jobs. And this last one, Jane, is a nurse educator in Boston seeking between $40,000 and $60,000. So the question is, how do we take what we know about Jane and what we know about the domain and turn it into a good search for Jane to help match her to the right documents? Well, if we turn Jane into a query, it would be really interesting to see what kind of results we get back. So in this case, I took Jane. I said, the job title she's looking for is nurse educator, so I'm going to do an exact match on the phrase nurse educator in the title field and give it a really high boost. And then I'm going to also match if I match either one of those words in the title somewhere. And also I'm going to look for, this city of Boston and state of Massachusetts, and if I match both of those, give a really high boost. Also going to look at the state of Massachusetts, even if it's not in Boston, maybe it's close by, and give that just kind of a normal boost. And then I'm going to apply a relevancy boost to the entire, if the salary range matches her, ideal salary range. So not all of these have to match, but the more that match, the higher my relevancy score should be. And so if I take a sample of documents and run this as a search against the search engine, what I get back is, number one, clinical educator, which is, what she's looking for, in Boston, matching her salary range. If you remember, she was nurse educator, Boston, 40 to 60,000. So the first one's a perfect match. The second one is, in Braintree, which is, nearby, and the salary is still within range. And the third one is also nearby, but the salary is out of range. So the search engine, just by turning what we know about Jane and her context into a query, was able to very accurately match results for her and effectively give her recommendations. So what we just did was use the search engine to basically build a content-based recommendation engine. And this is one way which we can leverage the content to increase relevancy. So this talk isn't really about recommendation engines. I have given a talk on recommendation engines in the past. You can definitely check that out. It talks a lot about collaborative filtering and other techniques as well. I think Doug Turnbull also gave a good talk here about them as well, so you guys can dig more into that later. But the general concept here is that there's a lot of ways, and he's right here in the front row. Welcome. The general concept within relevancy is that there's lots of ways that you can slice and dice what your users are looking for. In the upper left-hand corner here, we have traditional keyword search, which we described a few minutes ago. We've also got recommendations, which are either taking content we know about the user, like we saw with Jane just a minute ago, or taking feedback as users are interacting with documents, figuring out what kinds of things they're interacting with, and recommending more things like those, searching for more things like those. And there's also this idea of semantic search, which you see down here at the bottom, which is really understanding the intent of the user. When they type in a query and they type in words, what do those words mean, and how do I best represent them to the search engine to make sure I get the best results possible? So those are some key concepts that we'll see throughout the rest of the talk. So moving beyond normal search and even domain-specific search, leveraging traditional and basic keyword search, we now move on to taxonomies and entity extraction. One of my favorite projects that's not a part of Solr is the Solr text tagger. It's open source. David Smiley's worked on this, and you can download it. Effectively, what it does is it allows you to index a bunch of terms into an FST. It's basically it's a Solr index, but you can index a bunch of terms, millions and millions, and then when a document comes in, you can take that document and pass it to the Solr text tagger request handler, and it will, in milliseconds, identify and extract all of the terms that are in your index from that document. So it's just basically a really, really fast, naive entity extractor. And I'll talk more about how we use it in just a bit, but you can pass other things besides documents. You can also pass queries to this thing. And if you've got a taxonomy full of entities you know from your domain, and you take a query and pass it to this thing, it can highlight exactly where in your query each of those entities are found. And then you can do things like substitutions. Let me replace that entity with that entity or some expanded conceptual version of that entity. So a research paper I worked on back when I was at Career Builder, this one on the top, crowdsourced query augmentation, blah, blah, blah. It talks about some ways that you can go about finding entities within your domain. So if you already have a team that builds out a taxonomy or ontology, you're probably ahead of the curve, but there might be some things that you could do to improve there as well. you can use topic modeling or some sort of clustering algorithm to take your documents and find out the things that are interesting and relevant. You can also use statistical analysis of interesting phrases within those documents, using something like word2vec, and I'll talk about the DICE conceptual search piece in just a minute as well to do that. What I've done historically is actually had access to large amounts of query logs, which many of you guys have as well. And so this paper specifically talks about how you can mine your query logs to find the most interesting entities within a domain. And at a high level, you take all the things people have searched for, you roll them up and figure out what things people search for the most, remove the noise, and then you start with that as a taxonomy of things that people care about within your domain. You can feed those to the Solr text tagger, take new documents and queries coming in, extract those entities back out, and all of a sudden you've got the ability to actually identify entities and run more intelligent searches based upon them. And there's a couple of different kinds of, this is from a talk I gave last year, there's a couple of different kinds of entities you might be looking for. So there's synonyms, words that are either, that are spelled differently, but they actually mean the same thing, and you want to treat those as the same within your domain. There's ambiguous terms, words that have multiple meanings depending upon the context, and there's related terms, which are, you might want to expand to include them in a conceptual search, but they're not exactly the same thing. And so one of the other papers that I reference in here talks about how you can actually go about differentiating those as well. I mentioned a few minutes ago, if you don't have lots of query logs, you can actually use just your data itself to find interesting entities and relationships within your domain. One of the best ways I've seen to do that is using something like word2vec. And you basically can take your data, feed it to word2vec. It can extract out interesting keywords and phrases as well as vectors associated with them so that you can do additional operations on those. And Simon Hughes at DICE, actually about a year or two ago, maybe a year and a half ago, open sourced this conceptual search plugin for Solr. And if you haven't checked it out, I highly recommend it. It basically, he's got a set of scripts here that where you can take your data, run them through word2vec, generate synonym files effectively, generate those entities and then generate synonym files for them, and then use those as the basis for a conceptual search. So if you just want to kind of get started with very minimal investment, this is a good way to get started to be able to identify a taxonomy up front. There's also another project I want to mention called the Solr RDF project. So for those of you who are more used to dealing with RDF triples and searching sort of a pre-built knowledge graph, a lot of times you'll go and build something in Neo4j or use some RDF triple store. You can actually use Solr to do this directly. So if you add this plugin in, you can index your data in such a way that, that things are stored as RDF triples, and it is actually fully Sparkle 1.1 compliant. So if you are used to running Sparkle queries, you can actually run them against Solr directly and use Solr as a pre-built knowledge graph. So with all of those concepts, once you've built that taxonomy and have your list of entities and want to actually start extracting entities from documents and searching on those entities, the next step you move towards is query intent. So the first piece of that is query parsing. So there's actually Solr 9418 is a probabilistic query parser. It's basically a request handler where you can take queries as they come into the search engine, and leveraging the underlying inverted index in Lucene, you can figure out using Bayes' theorem, whenever I see, let me just flip to the next slide. Whenever I see a query come in, such as this one, senior Java developer Hadoop, how do I parse that? Get over here on the bottom left, there's the list of possible parsings, and the query could have been parsed in any of these ways, but senior Java developer as a phrase and Hadoop as a phrase is the best parsing of that example. And so this probabilistic parser that was contributed basically allows you to, without having a taxonomy, use your underlying inverted index and bubble up knowledge from it to be able to parse the query more intelligently so that you don't end up running a search for senior and Java and developer and Hadoop, which is what a basic keyword search would do. Instead, you're running a search for documents that match the exact phrase, the exact phrases that you're looking for. So it's just a more intelligent understanding of your search. You can download that patch and play with it today if you wanted to. This is an example of some of the math internally from a talk I gave last year, where you can kind of see what it's doing behind the scenes. The version I was using was different from the open source one, but the concepts are the same. The math is almost exactly the same from what I've seen. And once you've taken those things, once you've taken those two concepts of having an entity extractor with known entities and having a probabilistic parser which can identify entities you've never seen before, as long as they're represented in your inverted index, you can combine those two together in interesting ways. So from that paper I referenced earlier, over here on the right, we have an example of how the entity extractor works. So instead of passing in a document here, I'm passing in a query. Software engineer and Hadoop Java, I pass it into the entity extractor, and the Solr text tagger is able to tag exactly where in that query each of the entities in my taxonomy existed, and ultimately give me a tagged version of that query out of the bottom. So you've got software engineer and Hadoop and Java as three different terms effectively, which allows you to do more intelligent substitutions and manipulations of the query after that. And then this probabilistic query parser also allows you to further manipulate and understand things you've never seen before. And once you've done that, the next step, after you've taken your query, parsed it out syntactically into the phrases it represents, the next step is to be able to augment your query and inject additional related terms or phrases in, so that you're not just running a text search, you're actually running a conceptual search that searches for the meaning of what the user intended. So I mentioned the semantic knowledge graph earlier. This is something that just got open sourced maybe a month or two ago by CareerBuilder. It's a really popular, I say popular, it's been tweeted about a lot, but it's a really powerful capability to be able to leverage your inverted index and understand the strength of relationships between entities and phrases and concepts within your domain. And to give you guys a little bit of an idea of how this thing works, if you're referring back to the inverted index we talked about earlier, I've got two different versions of an index here on the screen in the middle. On the right, I've got my inverted index, which you guys are all familiar with. When I index a document, it maps all of the terms to a postings list containing all the documents and their positions. And separately, on the left, I've got an uninverted index, which is the inverse of that. It has every document mapped to every term that exists within that document. If you turn doc values on a field in Solr or Lucene, doc values are basically an uninverted index, if you want to kind of think of them like this. Or if you don't have them on, Solr can create an uninverted index in memory for you, and this is used for different kinds of faceting and those sorts of things. But the trick with the semantic knowledge graph is that by leveraging both of those indices, you can actually traverse very quickly back and forth between a term and the documents it's found within and other terms within the domain. And so effectively the way this works, this data structure view here is somewhat representative of the inverted index. You've got a skill of Java. I find all the documents that's found within, and once I've found those documents, I can now use the uninverted index to traverse from the document to other terms. So in this case, I'm going from skills to skills. So starting from the skill of Java, I can traverse to the skill of Java, skill of oncology, skill of Hibernate, or skill of Scala. And not only can I traverse to them, but I can figure out what the intersection and overlap between documents is. So from a set theory view, you see that Java, Hibernate, and Scala have some, at least they don't all overlap, but they've at least got some overlap between them, but that oncology is completely unassociated with them. And then from a graph standpoint, if you think of the semantic knowledge graph, I basically just did a traversal from Java to itself, Java across the has-related skill edge to the node of Scala, and Java across the has-related skill edge to the node of Hibernate, and then oncology is disconnected in that graph. So this is, thinking of this inverted index and the way this works as a graph enables you to do some really cool things if you think about traversing the graph and scoring those relationships. This is a multi-level traversal. So if I say I want to start with Java, I want to then traverse to Hibernate, and from Hibernate, I now want to traverse through the documents that it's found within to the title of software engineer, or the title of data scientist, or the title of Java developer. You can really think about all sorts of interesting ways that you can navigate between nodes, which are just terms in your index, and actually score those relationships. In terms of scoring, The math here is pretty simple. At each level of the traversal within this graph, you are ranking between any two terms how statistically likely they are. Excuse me. How statistically likely they are to appear together. So in this case, I took the word Hadoop, and I'm looking at a bunch of terms: Hive, Spark, .NET, bogus word, teaching, and CPR. If I take all of those things and ask the semantic knowledge graph, how related are these things in your index when you traverse this graph, what it tells me is that Hive has a relatedness of 0.97. It is very, very, very related to Hadoop. Spark, 0.96, is also very related, slightly less than Hive, but very related. .NET is positively related, positively correlated with Hadoop, but not nearly as strongly as Hive or Spark. Bogus word has no correlation whatsoever. It doesn't even exist in my graph, apparently. Not surprised. Teaching has a negative correlation, and CPR has a much more negative correlation. So some people in the software engineering realm are teachers, but not many of them have CPR as a skill. And so effectively think of the semantic knowledge graph as, instead of scoring relationships between a query and a document, as scoring relationships between a term and any other term, or a phrase and any other phrase, which is really powerful and gives you some cool capabilities. In this case, I'm doing a graph traversal from software engineer star, so like a wildcard on engineer. I say, start with this query of software engineer, find me the most related skills, or find me a list of top skills, and then rank those relationships. And after you've found the top relationships, now traverse again to these titles down below. Again, just some really cool stuff you can do there. So the example that's on the GitHub repo for this semantic knowledge graph is actually something similar. It's let me search for keywords of data scientist. I want to then find the top job title associated with the keyword data scientist, and then for that I want to find the top 5 skills. And I also want to include this one skill, Java programming language, just to see how it compares to the other skills that you found. This is the current syntax for this graph traversal. Once I've passed that in, you see that what comes back is the top job title matching the keyword phrase of data scientist is, no surprise, data scientist, because that's the job title. For that title, what are the top skills? Machine learning, predictive modeling, artificial neural networks, Apache Hadoop, and Java's in there because I asked for it, but you can see that its relationship is 0.76 versus Hadoop was 0.94. So all the other things that came back were much more highly related, but it also scored the relationship to Java for me. So it doesn't take much of a leap from here to figure out, now that I've taken a query and I've parsed it and I've extracted entities out of it, if I were to just ask this semantic knowledge graph that was built automatically for my inverted index, if I were to ask it, given that I found data scientists in my query, what things should I expand this query out to include? Here's a nice list right here just by asking the graph, hey, why don't you expand it to include some of these skills? And then your query could become data scientist or this list of skills, and you're doing more of a conceptual search at that point, because you'll match documents that maybe they don't include the phrase data scientist, but they're very conceptually related. So that's a good way that you can go about boosting and improving your relevancy. Once you've identified terms, another important concept is contextual disambiguation. There's 2 ways to do this. There's more than 2, but there's 2 ways that I'd recommend trying this. One is a research paper, the first one, Query Sense Disambiguation, Leveraging Large-Scale User Behavioral Data. This one basically involves mining your query logs, I'll flip over to the slide in a second. The other way is the semantic knowledge graph. So in the first, and this is what is described in the first research paper, if you take a word like driver that actually has multiple meanings, so driver occurs commonly with truck driver, Linux, Windows, courier, embedded, CDL, and delivery. 2 distinct meanings are represented here. One is transportation, delivering something, and the other is some sort of a software or hardware driver, but these things commonly occur together within your document. So if you just run a keyword search for driver, you're going to get back documents that contain both of these meanings. Similarly with architect, there's this notion of a software architect as well as a sort of building and design architect. So how do you disambiguate those meanings? So in the research paper, we basically took all of the users who were running searches from the query logs, classified them into the kind of user they were by their job title. So in this case, Java developer, .NET developer, healthcare, nurse, and then looked at the kinds of searches being run by the people within that group. And if what we saw was that the same keywords were being used across groups, then that meant that the word had one meaning. But if we found a distinct group with its own vocabulary that used that word in a different way, we could then call that word ambiguous and actually define two different meanings. So we created a probabilistic graphical model to do this, and then ultimately it just ended up segmenting the terms. What you could also do if you don't have tons of query logs is you could leverage the semantic knowledge graph for this. So instead of mining query logs and classifying users, you could take your documents and look for a classification on the document, and then segment out how related terms are within the context of that classification. So just like I showed you guys a minute ago with that data scientist example, if instead of pulling back one title of data scientist, I had to pull back multiple titles, then I could have actually seen which terms were related within each of the titles, and if those lists look very different, then all of a sudden I've found an ambiguous meaning and I can treat it differently. So the benefit of that is that you don't need to mine query logs, but the downside is if your data is noisy or not representative of your domain, then it's going to be dirty. It's not going to represent the user's intent, it's going to represent your content. So if you think your content is representative of user intent, then by all means use this. It's much simpler, but if your users are running crazy things or your content doesn't fully represent them, then you might want to try the first method, if you have enough query logs. And here's just an example, sort of using either approach. You can create these distinct meanings so that when somebody does run a search and you extract an entity out of your query, you can jump to the specific meaning and expand the query to that, as opposed to expanding it to every possible non-disambiguated meaning of the word. And this is just an example showing that once you have these different meanings, when someone runs the query, you can, depending upon the context, choose one of those different meanings. So in this case, if someone searches for Windows and driver versus courier or driver, driver has a distinct meaning in each of those cases, and the words that you expand out to and substitute there would change based upon the context of the query. So going back to content, collaboration, and context, this is an example where the context is really key to making sure you understand the user's intent. And kind of tying this all together, Lucidworks has a commercial product called Fusion that makes it really easy to build query pipelines. So I was playing around with some of this last week and basically trying to just run a query. In this case, my query was detergent for clothes. And the results on the right are what I was getting with basic keyword search, which was laundry detergent was at the top, great. But then the next two results were dishwashing detergent and another dishwashing detergent, which wasn't at all what I meant. So the idea was, well, if I expand these queries out to include semantically related things, what would I get back? And you see I just added a semantic concept expansion stage in here, and on the left, now all of a sudden everything coming back is laundry detergent. So just kind of a proof of concept that this stuff works. In terms of relevancy tuning, this is sort of the next level. If you remember that curve, this is the next level on that curve. And people have traditionally looked at precision and recall for measuring relevancy. The problem with that is, assume that you have a precision of 90% and a recall of 100%, but the 10% of relevant documents are all the ones that show up at the top of your search results. Your first page just looks awful. You don't really have good results. And so something like a discounted cumulative gain or normalized discounted cumulative gain tends to work a bit better for measuring relevancy in most cases. And the idea there is you've got some sort of ideal rank you're looking for, and you're going to be measuring, you do your discounted cumulative gain based upon a labeled data set of what order things should appear in, typically labeled by a data analyst, and then based upon that, you compare your actual relevancy with your ideal relevancy and look for ways to improve it. Learning to rank is one of the last topics I want to talk about. If you haven't seen, Bloomberg's got a learning to rank plugin that they've published, and I think it's actually pretty close to being committed to Solr. Fingers crossed, we'll see. The idea behind it, learning to rank in general, though, is when you run your search, you have these relevancy judgments, like I referred to on the last slide, that tell you what order a certain document should appear in. You use those relevancy judgments along with the features in your documents to train a ranking classifier that is able to then take a query and then take documents with a bunch of features and determine the relative order of those documents to the query and more or less you just re-rank documents after they've come back. So typically, you would apply learning to rank as a re-ranker. You run your normal search, your sort of base level search to get a list of candidate results to return, and then you re-rank the top 1,000, 10,000, some number that's reasonable to run the computation on, and then you return those back. And in all the academic literature and even in practice, I've heard really, really good things about, and talked with people and worked with people on projects who've gotten really good results from using learning to rank. But it's definitely something you should check out. Like I mentioned, it's Solr 8542 if you want to apply it to your version of Solr and use it. I do think it'll hopefully be committed soon, but feel free to download it and play with it. These are some common learning to rank algorithms, RankNet, LambdaMart, SVM rank. I think they recommend LambdaMart, or at least their examples do. But some fun stuff to play with there. And that's just an example of kind of building how LambdaMart builds a ranking tree. I'll skip over that. So one of the problems with things like learning to rank and even calculating NDCG and trying to do these relevancy judgments is that typically, in most of the use cases I've seen, it requires a data analyst to go through and tag all of the, to say these are the list of relevant documents for this query. It's a very labor-intensive process, but it can be done, and it is a good way to measure relevancy. So the pros of hiring employees, contractors, or interns to do tagging of a corpus like this are that you tend to get really good accuracy because they're typically domain experts and know what they're talking about. But the cons are that it's expensive, not scalable, and ultimately over time the data becomes stale. So another way to do this is to crowdsource, to find people on Mechanical Turk and tell them that, hey, for this query, here's a list of documents, rank them for me, tell me how relevant each of them are for this query. The pro is it's typically less cost and more scalable. The cons are it's less accurate, and the data still becomes stale. And so, one of the things that's really interesting to me is the question of, can you actually use reflected intelligence? Can you leverage your query logs to infer relevancy judgments? If you could do that, then you could do relevancy judgments across all of the queries in your domain and train a learning to rank classifier. You could take those relevancy judgments and build a QA system that actually checks to see how, for any different algorithm, if you want to play around with your relevancy parameters, how well is this one performing versus my base algorithm? And you can actually backtest and benchmark things based upon your query logs. So one way to do this, Microsoft has some literature on this, some academic research, and I've seen it from a few other folks. You can do this idea of a click and skip graph. So this is something I presented with a former colleague of mine from Career Builder earlier this year at a Georgia Tech conference. But the general idea here is that you look at the documents when a user comes in, they see document 1, they don't click on it. They see document 2, they click on it. They see document 3, they click on it, and then they don't go beyond that. What you can do is you can actually look and say, well, document 1 probably wasn't relevant because they skipped over it. But document 2 and 3 must have been because they clicked on it. But I'm not going to look at anything beyond document 4 because they probably just stopped looking at results after that. And by sort of counting the clicks, counting the skips, and then trying to look at this over lots of people and lots of queries, you can get back to that intuition that I gave you earlier of, hey, if someone's running a search and they click over a couple of documents and they click on the third one, that one's probably more relevant. That sort of intuition is built into this idea of generating a click and skip graph and being able to actually try to infer what the right ordering of documents is. And once you've done that and you've generated this sort of ideal relevancy ranking, for this query and this set of documents, here's the ideal ranking based upon what people actually clicked on and skipped over, you can do some really cool things in terms of trying to benchmark. So in this case, this lineup here is my default algorithm. And then say I want to just play around with a bunch of different algorithms and see how they perform. Here's my default. I've got my ideal ranking somewhere else, and I can actually backtest and just look at a bunch of algorithms and see how they would perform. It's a really good way of almost doing A/B testing with your users without actually having to expose your users to all these experiments. You can run a bunch of experiments, and the ones that look good, you can then show those to your users to A/B test them. So this, there's a lot of people working on this kind of stuff. I just mainly want to introduce you guys to the concept today and try to tie, a lot of these open source projects, a lot of these techniques, a lot of these pending patches for Solr, and just some sort of industry, kind of wisdom and knowledge, and just kind of pull that all together for you guys, and just to say that there's a lot of information in your content that you can expose through things like the semantic knowledge graph. And there's a lot of information in your query logs if you look at how users are actually interacting with your content. And ultimately, if you can take basic keyword search, build on top of that by adding taxonomies, introduce query intent and interpretation, semantic parsing, and then these relevancy tuning techniques, you're going to be in really great shape. But if you ultimately have the ability to take your users' feedback and learn from that and then integrate that into each of these steps, you can, at the end of the day, you can turn Lucene Solr into a self-learning data system where your user feedback influences the way that every other part of your system works. So some food for thought there, definitely some stuff worth checking out. And I think that's it. I'm Trey Grainger. If you don't have a copy of Solr in Action, there's a discount code, CTWLU Solr TW, I think. The slides will be sent out after, but you can use that for a bit to get a discounted version. And for two of you guys on Twitter, I'll let you know we've got some books for you as well. Signed by both me and Tim Potter, so there's a bonus there. I think that's it. I think I'm at time. If you guys have questions, feel free to grab me after. Thanks.